Greetings, this is Professor Roman, and we're continuing our lectures on linear algebra. We have looked fairly carefully at vector spaces and linear combinations, subspaces, and the four important concepts of spanning set, linearly independent set, basis, and dimension. And also direct sums, by the way. And now it's time to look at functions between vector spaces. I said in an earlier lecture that mathematics can be very generally described as the study of non-empty sets with a certain type of structure. Mathematicians believe that the study of any mathematical object or any mathematical structure, and that of course includes vector spaces, is only half complete without a careful look at the structure-preserving functions between such structures. In fact, there's an entire branch of mathematics devoted to this idea. It's called category theory, where the functions between objects, they're known as morphisms, play an equal role with the objects themselves. The structure-preserving maps between vector spaces are called linear transformations. So a function, we have two vector spaces V and W over the same field F, and it must be the same field. A function tau from V to W is a linear transformation, also called just a linear map or simply linear, if it has the following two properties. It is additive, which means that tau applied to a sum of two vectors u plus v is the same as tau of u plus tau of v. And we would refer to this informally as saying that tau preserves addition. Tau must also be homogeneous, which means if A is a scalar and V is a vector, tau of AV is A times tau of V. So we would refer to this as preserving scalar multiplication. It's not very difficult to see that these two properties are equivalent to simply preserving linear combinations, which would look like this. And I will use this symbol script L of VW to denote the set of all linear transformations from V to W. There are a few other notations, but this one's compact and I like it. A linear transformation from a vector space V to itself is referred to as a linear operator, or just an operator on V. And I'll denote the set of all linear operators on V by script L of V. A linear operator on a real vector space is called a real linear operator, and a linear operator on a complex vector space is called a complex linear operator. A linear transformation from V to its base field F, remember that F is a vector space over itself, this is called a linear functional on V. And the linear functionals on V are denoted by V star and called the dual space of V. I'm going to use, for the most part, Greek letters to denote linear transformations. So I would write tau of V or just tau V to denote the application of the linear transformation tau to the vector V. The parentheses sometimes are required if I want to write, for example, tau of u plus V, but not always required. We can extend the application of a linear map from the vectors in V to subsets of V in the expected way. If X is a subset of V, then tau of X is just the set of all tau of little x, where little x varies over the set, capital X. Bijective linear transformations have a special name. They are called isomorphisms. This is from the Greek, iso meaning same, morph or morphism is form, so same form. When there is an isomorphism from V to W, we say that V and W are isomorphic, and I will use this symbol for isomorphism. There are other symbols, but this one's quite common, I think. A bijective linear operator, tau on V, is called an automorphism. Some examples of linear maps: the derivative applied to the vector space of all infinitely differentiable functions on R is linear. You would have learned that in a basic calculus course. And similarly, if we take the vector space, say, of real polynomials, just for simplicity, the definite integral from 0 to x, tau of f equals integral from 0 to x of f of t dt. As x varies, this is a function, it's a polynomial, and in fact the integral is also linear. This is an important function. For an integer k between 1 and n, the function rho sub k, this is the Greek letter rho, mapping fn to the base field f, defined by picking out the kth component. This is a linear transformation from fn to f. In fact, it's a linear functional. Maybe I should say that. And it's called projection onto the kth coordinate. So projection is linear. You can add two n-tuples and then project and then pick out the kth coordinate, or you can simply add the two kth coordinates. And similarly for scalar multiplication. These are very important linear maps that we'll spend considerable time discussing. If A is an m by n matrix over F, then the map mu sub A, Greek letter mu, mapping Fn to Fm, defined simply as multiplication by the matrix, is linear. This is a linear functional. Be careful here about the parameters m and n. This is an m by n matrix, yet it maps Fn to Fm. This is called a matrix transformation. And we will, as I say, discuss this at some length. When m equals n, so we are multiplying by square matrices, the matrix transformation will be an isomorphism precisely when A is a non-singular matrix. If m and n are different, then the matrix transformation can never be an isomorphism. It will either fail to be injective or fail to be surjective. The transpose map on matrices is in fact an isomorphism. Here are two linear maps on the sequence spaces. The left shift operator does what it sounds like. It shifts all the terms in the sequence one position to the left. A1 disappears, drops off. So tau of A1, A2, and so on is A2, A3, and so on. The right shift operator goes in the other direction. You can see this should be sigma. It moves everything one position to the right and then puts a 0 in the first position. And these are both linear maps. Now let's let V and W be vector spaces over a field F, and let X be a non-empty subset of V. We're going to prove soon that the set L of VW of all linear maps from V to W is a vector space under ordinary addition of functions and scalar multiplication of functions. And we've already seen, example 1.11, that the set of all functions from X to V is a vector space. Now the restriction map, rho sub X, which takes a linear map from V to W and restricts the domain to X, that produces a function from X to W. And this is linear because if we restrict a linear combination A tau plus B sigma to X, we get the same thing as if we restrict tau to X, restrict sigma to X, and then take the linear combination after the restrictions are done. So the restriction map is linear. The determinant function, now we can, one normally from elementary linear algebra thinks of the determinant as applying to all square matrices. But if we fix a size n, then we can think of the determinant as mapping the n by n matrices to the base field. But we can also think of this map not as a function on n by n matrices, but rather as a function written this way on the rows of the matrix in question. So the determinant of R1 through Rn, where the R's here are vectors in Fn, is the determinant of the matrix whose rows are R1 through Rn. So just as a quick example, the determinant of this, if in this case n is 2, we have two vectors in R and say R2, let's say, then the determinant as a function of two vectors is the determinant of this matrix. There is great advantage at times to thinking of determinants as multivariable functions rather than as functions on matrices. One of the things you may have learned in elementary linear algebra is that if we take a matrix and we split, let's say we write the kth row as a linear combination of two vectors, then the determinant of this matrix is equal to this. A times the determinant of this matrix plus B times the determinant of this matrix. So what we've done is these are the two vectors that contribute to that row. So this means that if we fix all rows except the kth row, now the determinant is a function of that kth row. Everything else is fixed. It is linear in the kth row. So in terms of looking at the determinant as a function on n variables, it is linear with respect to each variable, assuming the other variables are fixed. This function, f, mapping f2 to base field f, defined by f of ab as the product ab, is not linear. But if we fix one of the variables, let's say we fix b, and we let a vary, then this is linear in a for a given fixed b. And here is the reason. We take a linear combination here. In the first position, apply f, we get this. So f does preserve linear combinations in the first position as long as b is fixed, doesn't vary. And a similar statement, of course, applies if we fix a and let b vary. So this function is linear in each variable separately. The other variable must remain fixed. Here is a simple result that we will actually use quite often, and I'm going to leave the proof for you as practice. Let tau map V to W be a linear transformation, and let S be a subspace of V. The restriction of tau to the subspace S is also a linear transformation. Also, if tau is injective, then so is the restriction. Now we come to one of the key features of linear transformations. One of the most important ways, and one of the most common ways to define a linear transformation, tau, from V to W, is to first choose a basis B for V, and then define a set function, f, from B to W. And finally, extend that set function to a linear transformation, which I'll denote by tau sub f, because it depends on f, from V to W. This process is called extension by linearity. And here's the way it works. The set function f that maps the basis B for V to W is really just a formal way to assign a vector in W to each basis vector in B. So once this assignment has been done, then since every vector in V has an essentially unique expression as a linear combination of basis vectors, let's say it looks like this, where the u sub i's belong to B, I should add that, then we can set tau sub f applied to V to be its tau sub f applied to this linear combination to be equal to this sum, where we are now applying f to the basis vectors u sub I. In other words, we're using the assignment that f provides. So these are vectors in W. This extension is well defined precisely because this is essentially unique, this linear combination. And the trivial differences of adding zero terms or reordering terms do not affect this expression here. So it is the fact that we are using a basis that makes this well defined. And to see that tau sub f is linear, we'll take two vectors in V. Now they are linear combinations of the basis vectors from B, but they may involve different basis vectors. And we can sort of fix that little minor issue by allowing coefficients equal to 0. We can beef up each linear combination so that they look like this, and they use the same vectors from the basis. Different coefficients, of course. Then we can write tau f applied to this linear combination of V and W. Looks like I need this to be a V, and I want this to be a W. Okay? So that is tau f applied to this linear combination, and then by definition of tau f, it passes inside but becomes f applied to the basis vectors. That we can split more, and then that's equal to alpha tau f of V plus beta tau f of W. And so that is linearity. So the set function f, any set function f from the basis B to W uniquely determines a linear transformation, tau sub f, from V to W. It's common to denote both this set function f and the extension tau sub f simply by tau. It's just more convenient to do that, and the context will avoid any confusion, really. This shows also, by the way, that if we have two linear transformations from V to W and they agree on the vectors in a basis, or put another way, if their restriction to the basis is the same function, then sigma and tau are the same linear transformation. If two linear maps agree on a basis, they are the same linear map. All of this is very important. It doesn't, in my experience, get enough emphasis in linear algebra classes. When I teach, for example, the second quarter of advanced undergraduate linear algebra, and I ask the students who took the first quarter, typically not my section of the first quarter, if they're familiar with this, they really are not, for the most part. And I think that's a critical omission. This needs to be emphasized. So in the summary here, this theorem, I have called the fundamental theorem on linear transformations, just to emphasize its importance. And it has two parts, and it goes like this. V and W are vector spaces over the same field F. B is a basis for V. Then part one, for every set function tau from B to W, there's a unique linear transformation tau from V to W that extends F. Oops. Extends tau. And this process is called extension by linearity. Part 2, a linear transformation tau from V to W is uniquely determined by its values on a basis. Or put another way, if tau and sigma are linear maps from V to W that agree on the basis, then they're the same map. Here's an example. This set of 3 vectors is a basis for R3. Therefore, I can do an assignment or make a set function, tau, that sends the basis vectors to anything I want in W. W in this case is R2, and I just made these up. These two are the same. This is different. It doesn't matter. As long as I put 3 vectors here that belong to R2, I have an assignment of vectors from W to each of the 3 basis vectors, and that can be extended by linearity to a linear transformation from R3 to R2. Another example, for the polynomial vector space f square bracket x, we can define a linear operator. All we have to do is specify what that operator does to a basis and then utter the words extend by linearity. So I'm going to send the standard basis vectors x to the power n to nx to the n minus 1 for all n. And that, the extension of this to a linear map is one you're quite familiar with. I said earlier that we would show that the set of all linear transformations from V to W is in fact a vector space. The operations are the usual addition and scalar multiplication of functions. And this provides a way to generate new vector spaces from existing ones as well, as the direct sum did, as we did earlier. So V and W, of course, must be vector spaces over the same field. We have seen in an example, an earlier example, that this set of all functions from V to W, denoted this way, W to the power V, is a vector space. Because W is a vector space, V does not need to be. It could be any set. In this case, it is a vector space. And in fact, L of VW is a subspace of this bigger vector space. This theorem restates that and adds a couple of other important facts. So we have 3 vector spaces over the field F. L of VW is a subspace of the vector space of all functions from V to W. And here's the specifics. If you take 2 linear maps from V to W and 2 scalars, the linear combination will also be a linear map from V to W. And that's relatively easy to check. I'm going to leave it for you. The composition of linear transformations is linear. I will also leave that for you. The inverse of a bijective linear map is linear, and also bijective, of course. And let's look at the proof of the third part. It's not too difficult, but there is a little bit of a key idea you must recognize. So tau is a bijective linear transformation, in other words, an isomorphism. Tau inverse does exist, and it's well defined from W to V. And here's the key idea. If we take two vectors, W1 and W2, in W, because tau is bijective, there are vectors V1 and V2, in fact unique vectors, for which W1 equals tau of V1 and W2 equals tau of V2. Therefore, tau inverse applied to the linear combination of W1 and W2 can be written this way, where I revert back to the vector space V here. This tau is linear, so it can be pulled outside here, and we get this. Tau inverse tau is the identity. We have this, and finally this. And that shows that tau inverse preserves linear combinations and is therefore a linear map. So we now know that L of VW is a vector space. What can we say about its dimension? In particular, when V and W are finite dimensional. Well, we can actually produce a basis, and that, of course, will tell us what the dimension is. So let's let B be the vectors V1 through Vn, be a basis for V, and C, the vectors W1 through Wm, be a basis for W. Then we can construct a basis for L of VW as follows. We define for each pair of indices, ij. So if you look at the picture here, here's V sub I and here's W sub j. These are the V's, the basis for capital V. These are the basis vectors for capital W. Fix a V sub I, fix a W sub j. Define a map tau sub ij that takes Vi to Wj, takes all the other basis vectors to 0. This is our set function, and it can be extended by linearity to linear maps from V to W, one for each I and j. So I have m times n linear transformations, the tau sub ij's. These form a basis for this vector space L of VW. There's different ways to show this, but one way is to show that every vector tau in L of VW, of course it's a linear transformation, has an essentially unique representation as a linear combination of the vectors in this set D. That's one of the characterizations of a basis. Or put another way, we need to show that there are unique non-zero scalars, Aij, for which tau can be written as a linear combination of the tau ij's with coefficients Aij. Well, the fundamental theorem on linear transformations tells us that tau is equal to such a linear combination if and only if these two linear transformations have the same value on basis vectors. In other words, tau of VW is equal to, in other words, there are unique non-zero scalars Aij for which this equality holds. This is the same as this, because tau ij of vk is 0 unless I equals k, in which case this is w sub j. However, the w vectors belong to C. It's a basis for capital W. So any vector tau of Vk has an essentially unique representation of this form. Well, so we now know that L of VW has a basis of size m times n. And so we can say that if V and W are finite dimensional vector spaces, the dimension of L of VW is the product of the dimension of V and the dimension of W. Isomorphisms, which as you know are bijective linear transformations, are used to express the fact that two vector spaces have the same vector space structure. And here's a simple example. Consider the polynomial space f square bracket x and f square bracket y. The only difference between these two vector spaces is the symbol that's used for the independent variable. So are these really different vector spaces? Well, as sets they are different, but from the point of view of the linear structure, the vector space structure, they behave exactly the same way. They are essentially the same vector space. For instance, their subset lattices are essentially the same. They have essentially the same bases, and so on. The only difference is a relabeling of the independent variable. And that can be expressed by a function, tau, from polynomials in x to polynomials in y, which simply replaces x by y. This is a vector space isomorphism. These two vector spaces are isomorphic, and from the point of view of linear algebra, they are essentially the same vector space. It would be a little inappropriate to say they're the same vector space because they're not the same set. And so how could they be the same vector space? So that's why I use the word essentially. Here's a little more interesting example. Take the polynomials of degree n or less over f, and take the Euclidean space Fn plus 1. We can define a map, tau, sending a polynomial to its ordered n plus 1 tuple of coefficients. The polynomial, of course, has to be written in this order. This is an isomorphism between these two vector spaces, and so these vector spaces are isomorphic. In other words, they are also essentially the same. Of course, a polynomial uniquely determines its coefficients and vice versa. Because tau is a bijection, but the vector space operations are compatible. You can add two polynomials and then just look at their coefficients, or you can first look at the coefficients and add those coefficients together, and it comes out the same. So let's take a closer look at this idea of how an isomorphism actually preserves vector space structure. Let V be a vector space over a field F, and let S be any set whatsoever, but that has the same cardinality as V. So there is a bijection sigma from V to S. We can use that bijection to transfer the vector space structure from V to S, which means we have to define the two vector space operations on S. As for, so if we take a little s and little t in S and a couple of scalars, we will define this linear combination, AS plus BT. That will take care of defining both addition and scalar multiplication at the same time, this way. Now, this looks a little messy, but what it amounts to is first pass from S back to V using sigma inverse. And because sigma is a bijection, the inverse is well defined. So sigma inverse of S and sigma inverse of T are vectors in capital V. We can take their linear combination using the same scalars. That's another vector in V. Then we ship it back by sigma. So we are, if you would like to say, borrowing the operations on V to use on S. Take vectors in S, ship them back to V, you use the vector space operations in V, then send back to S. So this process makes S into a vector space. And now it would be difficult to dispute the fact that the vector space structure imposed on S is the same structure as the one on V. Because we got the vector space structure on S from the structure on V. In a sense, really, we're simply relabeling the vectors in V in a bijective manner using the symbols in S. And the relabeling is done by the bijection sigma. Now suppose that we have a bijection between two vector spaces. Just a bijection. And V and W are vector spaces over the same field. We can use sigma, just as we got through doing, pretend that W is just a set. We can use sigma to transfer the structure on V to W. Now, there's no reason to believe that this transferred structure is the same as the original structure on W. We cannot say they're the same. But what if sigma was an isomorphism, not just a bijection? And we transfer the structure from V to W, so W has two structures. I'm going to denote the transferred structure, the operations, addition with a circle and scalar multiplication with a dot, so we don't confuse those with the original operations on W. Okay? Now, this is the definition of the transferred structure. Okay? Sigma is an isomorphism, so if we take A dot x plus v dot y. This is a linear combination of vectors in W using the transferred operations of addition and scalar multiplication. By definition, we ship x and y back by sigma inverse, we form the linear combination, then we ship back to W using sigma. Okay? But sigma is an isomorphism now, not just a bijection. So sigma will come inside and we end up with this. Therefore, the transferred structure and the original structure on W are the same. Same addition, same scalar multiplication. That explains why an isomorphism preserves the vector space structure. To say again, here's an isomorphism. This preserves the vector space structure because if we transfer the structure of V using sigma over to W, we get the structure that was already on W. And that's the preservation of the vector space structure. And that's why we say that V and W are essentially the same vector space. Just a relabeling. Going back to an earlier example of the polynomials of degree at most n and the n plus 1 tuples, these are isomorphic vector spaces. From a vector space perspective, whether we write polynomials in the usual way or as n plus 1 tuples doesn't make any difference because the vector space operations are the same either way. So a mathematician would say that these two vector spaces are essentially the same. And these ideas apply throughout mathematics, not just in linear algebra. In fact, this next theorem attests to the common structure that isomorphisms preserve. So if we have an isomorphism from V to W and a subset of V, then that subset spans V if and only if its image spans W. It's linearly independent if and only if its image is linearly independent in W now. And S is a basis for V if and only if its image is a basis for W. So all these structures, all these concepts are preserved. And finally, an isomorphism can be characterized as a linear transformation that maps a basis for V to a basis for W. And I'm leaving this a proof of this to you. A linear transformation tau from V to W is an isomorphism if and only if it maps some basis of V to a basis for W, in which case it maps all bases for V to a basis for W.